And we will move on to our second speaker. Our second speaker is Katinka van der Kooij. She's a postdoc in Jeroen Smeets' lab at the Vrije Universiteit in Amsterdam. And she will talk about a reach trajectory can be learned using binary reward feedback. So Katinka, take it away.
Yes. Spotlight and present. So I'd like to start by first thanking everyone for the opportunity to present here, for the room hosts for volunteering to do this, and especially the people in different time zones watching. I'll talk about reward-based learning of a little bit more complex reach trajectory. But what is reward-based motor learning? So imagine these girls practicing their dance move, and they're not sitting in front of a mirror, but they have to rely on their coach telling them whether they did it well or not. Well, that means that they have to engage in reward-based motor learning. They have to add variability, so they have to change their movements following failure. And when their coach tells them they are successful, they have to maintain that behavior. Well, this works well in simple tasks. But when many kinematic factors can contribute to performance, exploring all these different factors induces excess variability that hampers learning. Well, those familiar with reinforcement learning might think, yeah, but there's a way to solve that. When we have the binary reward feedback and many factors that can contribute to the reward, what you could do is you could solve a credit assignment problem. For instance, in the extreme case where only errors in slant would contribute to rewards, you could find out that this is the main factor to explore and only add variability in this factor. It is known that humans can do this for relatively simple tasks at least, but in our lab we also saw that 3D learning is much more difficult than 1D learning. So in this experiment, we wanted to ask, does solving the credit assignment problem for the participant by providing factorized feedback on one factor at a time improve learning? We used a trajectory matching task where participants matched a 3D trajectory they viewed in VR and where they received only binary, so red or green, performance feedback. We focused on two different factors, slant of the trajectory and also the length of the trajectory. And of course, is the composite of these two factors. There are two factorized groups and one non-factorized group. So the factorized group, so there was always a baseline phase without feedback, and we also ended with a phase without feedback. And in between, there were 3 learning sessions. So the factorized slant first group received feedback on slant first, then on length, and then on the composite. For a length first group, this was reversed. The non-factorized group, in contrast, received feedback on the composite of the two factors throughout the experiment. We wanted to ask, do participants in the factorized groups learn more? So does the orange group learn less? We measured learning as the difference between the absolute error in the baseline phase without feedback and the third learning phase. We started out using frequentist statistics, non-parametric tests, because we're dealing with absolute errors. And based on reviewer comments, we also added Bayes factor for interpretation of the strength of the evidence. So before we say anything about factorization, of course we want to know, can the factors be learned? I'll walk you through these graphs one by one. On the left, we have the composite, so the multi-dimensional task. What you see is in thick lines is the group medians going from baseline to the third learning phase. You see there's a lot of variability between participants. Therefore, the effects are difficult to see. A Wilkinson-signed rank test showed, however, that the composite task could be learned. Base factor showed that the evidence was only anecdotal. For the other two factors, we see similar results. So here we have slant, again, a lot of variability. Do I say it wrong? Yeah. A lot of variability between participants. Significant learning, and the same for length. Now let's look what happens with factorization. On the left, you have the factorized group. On the right, there's the composite group. And on the y-axis is learning. And learning is the difference from baseline to the third learning phase. We had expected that the factorized groups would learn more. Clearly, this is not the case. So we do find moderate evidence that factorization does not benefit learning. We found weak evidence that the ridge trajectory can be learned using binary reward feedback. I had to nuance these conclusions a lot based on the Bayesian evidence. In retrospect, we underestimated power problems in studying reduction of natural biases that vary between participants and also studying them in the multidimensional environment associated with a lot of noise. Thank you.
Thank you very much, Katinka. Yes, again, if you have questions, put them in the Q&A window and also indicate if you want to come on stage. Yeah, so, okay, JJ, you have a question? Go on.
Yeah, when I was, thank you for the talk first. Very interesting. When I was listening to your talk, it reminded me of this model framework called Optimal that is used in skill learning, for instance, for learning sport and so on, where they basically found that if you instruct someone to, for instance, pay attention on part of its body to perform a task, that person will do less than if you encourage this person to look or to at the the global movement or at the goal of the task. So you have to turn your body rather than make your hand like this and so on. And basically when they studied that more in sport and so on, they found that giving global instruction is much more efficient than giving detailed instruction about the movement. And so yeah, I wonder whether you feel that this is the same idea, that the fact that you don't really benefit from giving really the details. What's more important is really to have the global instruction, the global piece of information as feedback.
Yes, so what might be related, something that I looked at is, does performance decrease in the performance irrelevant factor? Visually, I thought I saw that, but there was no statistical evidence for that. But I think that definitely there are also theoretical reasons why you would think that you get a negative effect because performance in the irrelevant factors reduces.
Thanks.
Do we have more questions? So if you're in the audience, you can also raise your hand to come on stage and ask questions.
Otherwise, I have a question if there's none.
Yeah, sure. I mean, let's do it as interactive as possible.
Right. So in retrospect, we had this problem of dealing with participants starting at a different baseline level. Of course, we knew that before, but in retrospect, we also thought more about it. And I thought perhaps the right way to analyze this is with an analysis of covariance, where you use the baseline bias as a covariate. Would the audience agree with that?
Yeah.
Yeah. Are you saying when you're doing the pre-test, you're using the covariance structure to quantify the baseline performance, right? But I'm just saying, I also have the same problem when I doing those motor skill learning studies.
Yeah.
You found so huge inter-subject differences.
Yeah.
Sometimes we just want to calculate the mean or the variance, but it's just not enough. Sometimes it's really frustrated for that. So in fact, I just comments. This is a hard problem, and
yeah, hard. Yeah.
Yeah, unfortunately, the only way I did is the task you're using is actually complex because I'm also using virtual reality in a 3D space, and then we having trouble. So sometimes I trying to do those 2D tasks.
Yeah.
And I have a question for you. Is the I didn't get it. How did you do the factorization? Because in fact, you quoted one of my early papers with Gregory Dan. We also doing this kind of a credit assignment, but I don't know how did you do it?
How we did it. So we have a straight trajectory, slanted in depth, and we focused on the slant of the trajectory and the length of the trajectory.
You mean your score or your reward depends on the slant first, then
yes.
the. Oh, okay, I got it.
Yeah.
All right.
And the combination was just a factor difference.
Yeah, it's just in my 2013 paper is we found people can deal with those composite reward function.
Yeah.
They're just good at it. Yeah.
Yeah, so that I interpreted that correctly then, right? So that it looks like they can solve a credit assignment problem.
Yeah.
Or would you say something different?
I didn't see any difference. In your data, you also show the efficiency of doing that kind of credit assignment.
Yeah.
Okay, we have another comment from the audience. So Margaret Botsma says, we have turned to multi-level analysis to control for these baseline differences, studying the age effects on motor learning by adding participant as a random factor in the analysis. Margaret, if you want, you can also come on stage and discuss further. Okay, and I think Jeroen wants to come on stage. Ali, can you pull him to the panel? You're still muted, Jeroen.
Yes, well, I can comment in the meantime.
Yeah, sure.
When we go to these more complex analysis and considering the variability you have in more complex movements in 3D, we would have needed a huge sample size. So it's good to be aware of these things. I always love going more complex, but it comes with a cost of measuring many participants.
Okay. And that's already quite a lot. How many did you have there?
I had 20 per group, so that's not a lot. I come from a psychophysics background and it felt like a lot, but it's not.
Right.
Okay, unfortunately, I think Jeroen has disappeared again. We're also running a bit out of time, so thank you again, Katinka, and thanks everyone for this interactive discussion. And we move on to our last speaker.